All right, welcome to lesson 28 of the semester. We're getting pretty close to the end here. I think we have like 34 total or 33 or something like that. So we're getting close. Today we're going to continue talking about Taylor and Maclaurin series, which we introduced last time. And then this time what we're going to do is we're going to talk about the applications of Taylor and Maclaurin series. We're going to be doing that today and tomorrow. There's actually a decent number of applications of series right here. So we're just going to go ahead and start off with the applications that we've already seen. So we've already seen that series can help us do integrals that are either really difficult to do or maybe even impossible to do. And today we're going to look at some of the ones that are actually impossible to do analytically or by using techniques we've learned here. So let's say I want to do the integral from 0 to 1 of sine of x squared dx. Now, let's say I want to approximate this to an accuracy of 0.001, so 1 in 1,000. All right, now this integral might look a bit familiar right here. This is the integral that I wrote down on the first day of class. So I gave this integral as an example of one that even when we've gotten through the entire class, through all the integration techniques, we wouldn't be able to do this integral. And it's not because like we're holding stuff back, like, oh, there's a secret technique out there we haven't taught you, or it's not because like, oh, you know, Dr. Manley sucks at math. There's someone who can do this integral. Nobody can do it. Nobody can do this integral analytically, at least to my knowledge. I'm pretty sure they proved that you can't do this one analytically. But anyways, what we're going to do is we're at least going to be able to approximate this. So what we're going to do is we're going to write sine of x squared as a Maclaurin series, and then we're going to do the integral of the Maclaurin series. Now, doing the integral of a series, as we've seen, is always easy because we always just have to use the power rule here. So first of all, let's find a series for sine of x squared. And to begin with that, we need to remember what our series for sine of x was. So last time, the series for sine of x we saw was negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is the Maclaurin series for sine of x. It's centered at 0. We don't have x minus any numbers to a power here. And you guys remember the interval of convergence of this? What was the IOC for this one? It was all real numbers, right? So we don't need to worry about 0 or 1 being in the interval of convergence because it's going to be all real numbers here. All right, but we're not concerned with sine of x. That is something we know how to integrate. We're concerned with sine of x squared here. So sine of x squared is the sum from 0 to infinity of negative 1 to the n x squared to the 2n plus 1 over 2n plus 1 factorial. But a nicer way of writing this, oh, the mic's messed up. Okay. How about that? Is that better? Better? Okay, good. It seems like the first 5 minutes of class, like it always messes up somehow. This happens in my other class too. I don't really get what's going on. But anyways, another way we could write this is negative 1 to the n x to the 4n plus 2 over 2n plus 1 factorial. So this is going to be sine of x squared. And the interval of convergence for this will also be all real numbers here. All right, so now we have our series for sine of x squared. So this means that anytime we want to use sine of x squared, we can instead substitute in its power series or its Maclaurin series. So this is the sum from 0 to infinity of negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. Now remember, the nice thing about series is that the integral ignores almost every part of our series here. The only part that really matters is the polynomial part. Oops. So this will turn into the sum from 0 to infinity of negative 1 to the n, and then we have the integral of x to the 4n plus 2. All right, and then all we need to do here is just do the power rule on x to the 4n plus 2. So this will be, this was an aside here. This will be the sum from 0 to infinity of -1 to the n, x to the 4n plus 3 divided by 2n plus 1 factorial, and then times 4n plus 3. And this integral goes from 0 to 1 right here. All right, so now I'm going to go ahead and plug in 1 and 0. If I plug in 1 in for x, well, 1 to any power will be 1. So we end up getting this. And then I plug 0 in here, and 0 to any power is 0. So we don't need to write that part. So there we go. So we find that the integral from 0 to 1 of sine of x squared actually is doable, but we need to use series to do it. And it ends up being this series as our result right here. Now, as I said in the very beginning when we first started talking about series, in general, it's hard to know the exact sum of a series. So unfortunately, I don't really know of any way to turn this into a nice number like √2 or pi or anything like that. So we're kind of stuck with this series as an answer. But remember, it's actually not too hard to approximate an answer using only the first few terms of the series. And we saw last class, or I think 2 classes ago, we don't need very many terms to get a good approximation. So our goal for this problem is to get it to an error within 0.001 or 1 over 1,000. Now, thankfully, this is an alternating series, so we could use the alternating series remainder estimate to help us do this. So what we do is we call this part, the stuff that's not the alternator, a sub n. And then we make a little chart with n and a sub n, and we keep going until this ends up being smaller than our error threshold. So let's start with 0. So if I plug 0 in here, let's see, I have 1 over 1 times 3, so that's 1/3. Okay, got a ways to go with that. Next, I'm going to plug in n equals 1. So I have 1 over 3 factorial times 7. Now, 3 factorial is 6. So 6 times 7 will give us 1 over 42 here. All right, now let's plug in n equals 2. We have 1 over 5 factorial times 11. 1 over 5 factorial times 11. Does anyone know what 5 factorial is? Does anyone know that one off the top of their head? Yeah, it's 120, right? We have 120 times 11, which is 1 over 1320. But even if we didn't want to do that multiplication, we can kind of guess that 11 times 120 is going to be bigger than 1,000. So this number is less than 1 over 1,000. Now remember, once we reach that point, we just add together all of the terms in the series that come before this one. So our error for this, 0 to 1, or our approximation for this will be where we have n equals 0. So that'll be 1/3. And then we have n equals 1, and we include the alternator this time, so it's going to be minus 1 over 42. So this is going to be our approximation for our integral right here. And we know that the true value of this integral, whatever it is out there, is going to be within 0.001 of these terms right here. So while we can't get a nice exact value for this, we can get a pretty good approximation value with only 2 terms here. So it doesn't take very long to get a good approximation. Why do we subtract what we add? Well, we're doing the integral is the whole series right here, including the -1 to the n. So we take n equals 1 and put it in here, we have -1 to the first power. So that's why we have that minus sign there. All right, so this is kind of similar to what we did with the other series. The only difference is that I think those integrals were technically doable. It's just they were hard. This integral is not doable by conventional means. You have to use series to do it. All right, so let's take a look at something else that's also not doable using conventional techniques. And I want you guys to practice this one. I want you guys to try to do the integral from 0 to 1/2 of e to the negative x squared dx. And I want you to do this to an accuracy. So I want you to approximate to an accuracy of 0.01. 0.001 right here. All right. Can I go over how I got the 4n plus 3? I just did the power rule here. So I did the power rule of x to the 4n plus 2. I bumped up the power to be 4n plus 3, and I divided by the new power. All right, why don't you guys give this one a try? And just some context for this. To be honest with you, I don't really know an application where you would integrate sine of x squared. I certainly know an application where you integrate e to the negative x squared, and this comes from the bell curve in statistics. The bell curve follows the formula e to the negative x squared. So if you want to find the area under the bell curve, this would be an integral that you would do. Well, oh, sorry, yeah, I need to tell you, what's the e to the x sum? E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. Yeah, sorry, I forgot to include that. Can we do the factorial of negative numbers? Not really. Factorials are only defined for non-negative integers, but there is something called the gamma function that lets you do factorials of non-whole numbers. But we're not going to talk about that here. That's a little too far away from what we're doing. So the minus in the sum goes exactly where the x is. So it'll be negative x squared, all of that raised to the n. And that will simplify to be negative 1 to the n, x to the 2n. Is that what you're asking? If you're putting it in where the variable was, then yeah. Yeah, that's right. That's what you're going to do. Let me give you guys another minute or so, and then we'll go over how to do this. Diego, that's close. You just, the power on the -1 to the n should just be n. The -1 isn't raised to the 2n or anything like that. All right, let's see how this is done here. So the first thing we need to do is we need to come up with a series for e to the -x squared. So kind of like in the previous problem, what we're going to do is we're going to substitute in -x squared in for our variable here. So e to the -x squared will be the sum from 0 to infinity of -x squared to the n over n factorial. All right, now if I distribute the nth power to the x squared and to the negative here, I end up with n equals 0 to infinity of -1 to the n x to the 2n over n factorial. So this is going to be the series that I'm going to put in my integral. So the integral from 0 to 1/2 of e to the -x squared is the same thing as the integral from 0 to 1/2 of the series sum from 0 to infinity, -1 to the n, x to the 2n over n factorial. Now remember, all the integral does is it only affects the x to a power. It doesn't affect anything else, anything without x's. So we're just going to raise x to the 2n. We're going to raise that power by 1. So it'll be x to the 2n plus 1. And then we divide by our new power. So we divide by 2n plus 1 here. And since we're doing a definite integral, this goes from 0 to 1/2 here. All right, and then finally what I'm going to do is I'm going to plug 1/2 into here. And then I have n equals 0 to infinity, -1 to the n, 1/2 to the 2n plus 1 over n factorial times 2n plus 1. And this right here is the exact value of our integral right here. This is the exact value if we have all of the terms added together. Well, Gabriel has a question. Do we always get -1 to the n when we do these? That's a very good question. And the answer is no. And we're going to talk about how to deal with that in the next problem. But anyways, for now, since we do have a -1 to the n, we could use the alternating series estimate to get an approximation of this that has an accuracy of 1 in 1,000 right here. All right. So let's go ahead and do that. So remember this part right here, everything except the alternator will be our a sub n right here. Is there a way to simplify that? Yeah, another way you could have written this is you could have moved the 2 to the bottom here. And this would have been -1 to the n over 2 to the 2n plus 1, n factorial, 2n plus 1. So you could write it like that if you want. All right, now my goal here is to keep going through these terms until I get one that's going to be less than 1 over 1,000. All right, so let's plug in 0 for this. I have 1/2 to the first power, so it's a half. 0 factorial is 1, and this is 1. So I get 1/2 for this. All right, let's go ahead and move on to 1 here. I have a half cubed, which is an 1/8. And then I have 1 factorial times 3. So that's just 3. So I have 1/8 divided by 3 is 1 over 24. All right, we're still not there yet. Need to keep going. Let's try n equals 2 now. So if I put n equals 2 in here, I have 1/2 to the 5th. So 1/2 to the 5th. And then I divide by 2 factorial, which is 2. And then I multiply by 2 times 2 plus 1 is 5. So let's see. If we combine all of these together, we end up getting 1 over 320. All right, now hopefully the next one will put us less than 1 over 1,000 here. So let's see here. This one's going to give us 1/2 to the 7th over 3 factorial, which is 6, times this number, 2 times 3 plus 1 is 7. So this is going to be 1 over 42 times 2 to the 7th. And I don't know exactly what number that is. I'm very confident that this is going to be less than 1 over 1,000 here. So as long as you know that the number is going to be less than 1 over 1,000, what is it? It's 1 over 5376. Yeah, okay. Yeah, so we're definitely good in that front. All right, so we could stop here. And this means that our integral from 0 to 1/2 of e to the negative x squared dx will be approximately equal to 1/2. And then it's an alternating series, so we do minus 1 over 24. And then we flip the sign again, and we have plus 1 over 320. And we know that this result will be within 0.001 of the true value of this integral. Yeah. That's right. So the question was, for whatever n value we stop at, do we just use the terms up to and before that point? And that's absolutely right. So we used 1/2, 1 over 24, and 1 over 320 here. If it wasn't an alternating series, would you add them all? Yeah, I'm gonna get into that question here. So if it's not an alternating series, then the way we're gonna do this is different. So yeah, you may have noticed that conveniently all of these have been alternating series, but there are Taylor and Maclaurin series that are not alternating series here. Okay, so how do we compute error for a non-alternating series? Because we won't always be lucky. The series won't always be alternating here. So this is where something called the Taylor remainder estimate theorem comes in. Okay, so this is going to be kind of similar to the alternating series remainder estimate, whereas this gives an upper bound for our error. Okay, so suppose we use the nth partial sum S sub n of a Taylor series in place of the whole series. So what I mean by this, so back in this example here, we used n equals 0, n equals 1, n equals 2. So we used S2. This is S2 right here. We used S2 in place of the entire series. Now, it's going to end up having some error because you're missing a bunch of terms here, but it's at least a decent approximation. So what happens if we do that for a non-alternating series? Then the error, which is going to be called absolute value of Rn, and this is called the remainder. That's why it's R. This is going to be less than or equal to m times the absolute value of x minus a to the n plus 1 divided by n plus 1 factorial. So this is going to be our formula now. Now you can kind of see this is a little bit similar to the alternating series one. So remember, when we have n here, our alternating series error is always less than an plus 1. And we do see some n plus 1s here, but this ends up being a little bit more complicated. Now let me explain what all of these are right here, where a is the center of the series. So the center of each of the series that we did back there were 0, but we've seen non-zero centers before. X is the value we plug into the series. So for example, back here, our X would have been 1/2 for this one. So X would have been 1/2. And then M is a little bit different. M is kind of specific, where M is a number. And this is kind of the tricky part. M is a number such that M is greater than or equal to the n plus first derivative of our function at some point C. So let's say n is like 3, for example. Then we look at the fourth derivative of our function, and M needs to be bigger than the absolute value of that. Now what's C? C is in between A and X. So C could be any number in between A and X. So M just needs to be bigger than this derivative is. It needs to be guaranteed to be bigger than this derivative here. And this is what makes this method kind of annoying. It's in general hard to pick M. So that's what makes this method kind of inferior to the alternating series remainder estimate. So my advice to you right now is that if you can ever use the alternating series remainder estimate, I would use that in favor of this. I would only use this as kind of a backup in case you don't have an alternating series. All right. Now, by the way, for the Taylor series, the partial sums have a specific name. I want to talk about that too, because you see this name more often than Sn here. So for Taylor series, Sn is called the nth degree Taylor polynomial. So this is a term we'll be seeing a decent bit. And instead of writing it as Sn, we're going to write it as T sub n of X. And this will be some polynomial. Okay, this is all a bit abstract. So why don't we ground ourselves and actually do an example here to illustrate what's happening. Okay, so use the Taylor remainder estimate to find an upper bound on the error for using the second degree Maclaurin polynomial for e to the x to approximate the square root of e. Okay, let's digest this a bit. Let's see what's going on here. So we're going to make some kind of approximation, right? Let's say that we are a calculator and we need to calculate the square root of e. So some human punches in root e and we need to spit out a bunch of decimals for that. Well, we're a calculator, so we're not very smart, right? All we can add, subtract, and divide and multiply. That's all we could do. So we understand what polynomials are. So we're going to use a polynomial approximation of e to the x, and we're going to plug in 1/2 because root e is the same thing as e to the 1/2 here. Oh, sorry, this looks like using. There we go. Okay, so first of all, we need to find the second degree Maclaurin polynomial for e to the x, and then we're going to plug in 1/2. And then we need to find out how wrong we are, because we don't want to spit out a number that's too far away from the square root of e. Okay, so remember the series for e to the x is the sum from 0 to infinity of x to the n over n factorial. Now, if we were to start writing out the terms right here, I would plug in n equals 0. I have x to the 0 over 0 factorial is just 1. I plug in n equals 1, and I have x over 1 factorial, which is x. I plug in an n equals 2, I'd have x squared over 2 factorial, so x squared over 2. I plug in 3, I have x cubed over 3 factorial, which is 6. And I have x to the 5 over 120, and so on. Now, what I want to do is I want to use the second degree Maclaurin polynomial. So what I'm going to do is I'm going to say that, well, e to the x is exactly equal to all of this. Maybe it's at least approximately equal to 1 plus x squared over 2. So it's not going to be exactly equal because we're missing all these guys back here, but maybe it'll at least be close to 1 plus x squared over 2. So this is the second degree Maclaurin polynomial. And it's called a Maclaurin polynomial because this was a Maclaurin series that this came from. Now what we're going to do, since e to the x is approximately equal to this, I guess we can conclude that e to the 1/2 will approximately equal 1 plus 1/2 plus 1/2 squared over 2. And if we do this out, let's see, this is 1 plus 1/2. This is plus an 8. So I think this will be, what is this? 13 over 8. So our approximation for the square root of 8 is that it's pretty close to 13 over 8. And that's something a computer can spit out. A computer could do a decimal for 13 over 8. Okay, now the problem is that this isn't an exact answer. We're missing all of these terms that we need to plug 1/2 into. So how far off are we? Now the problem with this series is that this is not an alternating series. We can't use the alternating series remainder estimate. So I guess we're kind of forced to use the Taylor series remainder estimate here. All right, let's check what the formula for that is. So our error, remember this is our error here, this Rn thing, that's the error. So our error will be less than or equal to, well, it's hard to write them both. Yeah, I'm looking at this formula here and I'm copying it down here. So it seems like our error is less than or equal to m, absolute value of x minus a to the n plus 1 over n plus 1 factorial. Okay, now let's try to use that general formula in this specific instance. So let's see here. Let's cast all of our characters here and see which one is which. So what is our A going to be for this problem? What is the center of our Maclaurin series? It's 0, right? Yeah, so A is going to equal 0 for this one. Okay, now what x did we plug in order to make this approximation? We plugged in 1/2. That's right. Okay, so we know what that is. Now we did a degree 2 Maclaurin polynomial, so n is going to equal 2. All right, so far so good. So we got x, a, and n. That takes care of all of this. But now we need to get what m is here. Why is 0 the center? Because this is a Maclaurin series. So this is just x to the n. If this were centered somewhere else, like let's say we had, I don't know, like the sum from 0 to infinity of n times x minus 1 to the n or something, this would be centered at 1. So whatever number we're subtracting from the x inside here is our center. And if we're not subtracting any number at all, then our center is 0. All right. But now we need to figure out what this m is. And remember, m is the annoying part of this method. This is why we don't like this method very much. So according to our definition from way back when, m needs to be greater than or equal to the n plus first derivative of our function with this number c plugged in, where c is any number in between 0 and 1/2 in this case. So for this problem, c can be any number between 0 and 1/2. N is the degree of the Maclaurin polynomial we take? Yeah, that's right. So it's the degree of the approximation. All right, well, let's see here. So in this problem, our n is 2, right? So this will be the third derivative with our function plugged in. Well, let's see. What was our function? Our function that we found the series of was e to the x, right? Now, thankfully, that function has easy derivatives. If we take a derivative of e to the x, we end up with e to the x every single time. So it stands to reason that if we take 3 derivatives of e to the x, we're just going to have e to the x still. So this is going to be the absolute value of e. And then it has c plugged in for its x. So this is e to the c. Okay. Now, we can get rid of the absolute values here because e to the c will always be positive. All right. Now, c is going to be less than or equal to 1/2. So this number is less than or equal to e to the 1/2. All right. Now, what I'm going to do here is we're calculating something involving e, right? So in theory, if we're like a dumb calculator, we don't really know what e is exactly. But we can at least assume some basic information about e. And the basic information I'm going to assume is that e is less than 3. I'll take that as a fact that everyone knows that e is less than 3. So we're going to say that this is less than 3 to the 1/2. So this means that my m will end up being the square root of 3 right here. I know that this m, if I follow these inequalities, is guaranteed to be bigger than or equal to the m plus first derivative at c. So it's kind of this weird convoluted process where we need to kind of go through these inequalities right here, kind of like the direct comparison test. We go through inequalities until we find a number that's familiar for us. And I guess root 3 will be familiar enough here. So our m is going to be root 3 for this problem. All right, let's return to our error here. So this is going to be less than or equal to, and let's plug everything in. We have root 3 times x minus a, so 1/2 minus 0 to the m plus 1, so that's 3. And then we're going to divide by m plus 1 factorial, so that's 3 factorial. So our upper bound for the error on this is going to be root 3. Let's see, we have 1/2 cubed. 1/2 cubed is 8 times 3 factorial. We have root 3 over 48 right here. All right, so our error is going to be less than or equal to this. Now, compared to some of the other error bounds that we've gotten, this one is a bit less impressive than like 1 over, I think we got 1 over a billion, one class or something like that. Yeah, this one's a bit less impressive than the other ones. So in addition to being harder to use, the Taylor remainder estimate also doesn't give us quite as like cushy of a margin for our error. It actually, or rather it's the other way. It gives us a possibly larger error here. So it's not quite as good. So this is definitely kind of a backup method. We really want to use the alternating series remainder estimate. Where did the C inequality equation come from? It just comes from what m is, which is this. M just needs to be a number that's bigger than or equal to this right here. And so for our problem, n plus 1 was 3. And our problem, C ranged from 0 to 1/2. So this could be at most 1/2. And then we know that E is less than 3, a familiar number. All right, so there we go. So we got an estimate, but it's not quite as good as we'd like. So this one's going to be like a slanty face. Like, it's okay, but it's not super great. All right, so I want you guys to practice using this method. Now, don't worry, you're going to use the same function. So your m will be pretty similar to find for this. So use the third degree Maclaurin polynomial to approximate e squared. And then find an upper bound on the error. And for this one, we're going to use the fact that e is less than 3. Can we use e to the 0 to reduce the error for the previous problem? Well, not really, because C could be bigger than 0. So e to the, like, you, for example, we could have like 1/4, for example. So like e to the 1/4 would be bigger than e to the 0. So unfortunately, we can't do that. Why couldn't we just pick a ridiculously large number for m? Well, the problem with that is that that would influence this right here. If we pick a really big m, like say 1 billion or something, then we would have 1 billion over 48 as our error bound. And I don't think we want to be like 200 million or 20 million or whatever away from our value of e. So that's, so we usually want to pick the smallest possible m that would work. So let me write that. That's actually a good thing to remember. Pick smallest m that will work. Because it helps with our error to have a small m. Do you need to know what e to the x is as a series? Well, you need to figure out the 3rd degree Maclaurin polynomial in some way. So knowing what the series is would definitely be helpful with that. We find n. N is just the degree of the approximation. So n is going to be 3 for this. How do we know that the last one was centered at 0? Anytime they say the word Maclaurin, you know it's going to be centered at 0. But even if they didn't say Maclaurin, it's just x to the n. If it were x minus some number to the n, then it would be centered somewhere else. C is any number in between x and a. So you need to find x and a first, and then c can be any number in there. But you need to make sure that m is bigger than any value of c plugged into this function. Seems like people get 6. All right, let's take a look at this, and then hopefully we'll have enough time to do our last application here. So I want to use the 3rd degree Maclaurin polynomial. So we go back up here, and we have our Maclaurin series. So we just go out to the 3rd degree this time. So I'm going to say that e to the x is approximately 1 plus x squared over 2 plus x cubed over 6. So this tells me that e squared will be approximately 1 plus 2 squared over 2, which is 2, plus 8 over 6. So what is this going to end up being? This is 38 over 6, 19 over 3. All right. So we're saying that e squared is approximately 19 over 3. Okay, now how approximate is that? What's our upper bound for our error? So our error is less than or equal to m x minus a to the n plus 1 over n plus 1 factorial. Now in this problem here, our n, the degree of our approximation, is going to be 3. Our center of our series is 0 because it was a Maclaurin series. The number we plugged in to make the approximation was 2. And then now we need to get what m is. So in this problem, well, in general, m needs to be greater than or equal to the absolute value of the n plus first derivative with any possible c plugged in. Where in this problem, c could be any number between a and x, so from 0 to 2. Now let's see, once again, we're taking a bunch of derivatives of e to the x, so all of those will be e to the x. So the fourth derivative of this is e to the x, and then we plug c in here. All right, we can get rid of the absolute value because e to any power is always positive. C can, like this gets bigger, the bigger c gets, so at most, this will be e squared. But it would be a little bit silly to have our m be e squared because that's the number that we're trying to compute anyway. So we can't really have that as our m. But we could use the approximation once again that e is less than 3. So this is less than 3 squared, which is 9. So it looks like our m is going to end up being 9 right here. All right, that finally allows us to compute our error. So our error will be less than or equal to 9 times 2 minus 0 to the 4th power over 4 factorial. So let's see here. Let's see, 2 to the 4th is going to be 16. All right, so this is 16 times 9 over 24. Oh, this is 2/3. So this is going to end up being 6. So get a load of this. So our approximation was 19 over 3, right? And that's a number that's pretty close to 6. 18 over 3 is 6. So we have 19 over 3. This number is close to 6. But our error, we could be off by plus or minus 6. So what we're saying is e squared ranges anywhere from 0 to 12. And that's not really that useful. So the last one was a slanty face approximation. This is a frowny face approximation. This one was not very good at all. We would need to add more terms to our approximation for this to be better. All right. Oh, I only have 1 minute left. So the last thing I wanted to do today in class was I mentioned earlier in the semester as kind of a joke or as like a meme that the sum of all of the positive numbers is going to be equal negative 1/12. You may have seen this floating around the internet or videos or things like that. But I don't think we have enough time here to do that today. So I'll just do that in the beginning of next class. I think we're going to have extra time in the beginning of next class. So we'll just do that part then. We'll do it at the end of, yeah, we'll do that next time. But anyways, I will see you guys on Friday where we will do that and our other application.
Goodbye. Thank you.
Yeah, see you later.